Well, I actually want to make. Did you notice that I have graded the quizzes for mass balance and kinetics? Okay, probably you didn't notice. Yeah, they were done on Friday. So I just want to make a comment. I, I, I was glad that there was a lot of hundreds in there, and more than the hundreds, I was glad that many of you are doing way better. Um, it's not a surprise. Chemistry is always more difficult, and also many of you have been coming to office hours, and I've been giving you suggestions to study, and it might be what is working. Um, can you hear me?
Yeah.
Okay, I don't know what happened. My computer is gone. I don't see anything on my screen. So give me. I had lost the connection. So let me see if I can make it come back. It seems that it's working, but because you can hear me. If it doesn't work, what I'm going to do is just continue with the iPad. All right. Let's just continue with the iPad. You can hear me. I don't know if you can see me, but I don't see anything on my computer. All the screens are black. All right. Well, let me continue. Regardless of, I'm glad if you, well, you can't tell me you don't see me anymore, so I won't know if you're gone. So I just wanted to make a comment related to mass balance. Um, eh, Most of you did really well. Some of you didn't, and some of you did some uh, mistake related to the diagram that I think that it was very important to bring up. So I'm not going to talk about concentrations. Again, the problem was different for every single one because I set it up that way. I have a program that gives me different problems. So overall, can you confirm that you can see my iPad?
Yeah, we can see it.
Okay, thank you. Uh, oh, I'm back. All right. So uh, the system had two streams coming together. Well, actually, let me just model this differently. It said there was a river and there was a snow melt coming in. So we just, for the practice of the exercise, or river is going to have a flow and the snow melt is going to have a different flow. Okay, I'm not going to solve the problem, but some of you have some issues modeling the system. This is in general what you needed to model. It could be modeled different ways with a big, like I was trying to do it like this. But if you do something like this, then you need to acknowledge that the two streams come in. And the mistake that some of you made is just model this as the stream coming in, and it was confusing, so it was not correct. There's no melt. The Q somehow was in here with the concentration of the salt inside, and then solve for this system, and this is not correct. So make sure that you read the statements clearly, and if you see two different concentrations and two different flows, and it says they're going in, probably that's suggesting they're going in out. So it could be going out, so we just be very careful that it's one comma and then it's divided in two. That could possibly happen too. But that was not the situation in this problem. So you just want to make sure that this situation, uh, you know who you are and you see your problems. This is not correct. The approach that is correct is this one. And is there was some of you did conversion factors issues with liters and meters, cubic meters, and that's why the problem was not fully correct. Points deducted, but overall it was an easy problem. But the response that's given by the students was really good. So I'm very happy, and I'm glad that now your work is showing that you're working in a way that is helping you better to show that you're learning. Okay, is there any question about this mass balance problem? So just to make sure that everybody sees the opportunity, many of you are coming to my office hours. Some of you ask me questions, show me your work. That's very important. So you come to see me, bring your work, show me what you're doing, and ask me questions, and I'll ask you questions, and I'll help you that way. So it's more dynamic, and it's interactive, more interactive. So please come, especially if you don't know how to improve on study. Okay, so I just wanted to double check that this was clear because the test is coming Wednesday, and I want to make sure that you can prepare and maybe use that problem to study for the test. All right. So we're gonna continue with air pollution. Last time we were reading this problem. This problem is related to designing a settling chamber. Do you remember what kind of particles we talked about to treat last time? Where are these pollutants located? No. Mm, we talk about two types of particles in the air, right? The gas and the particulate matter. And this particulate, these two types of particles specifically are being looked at for point source pollution. So we're going to start with point source pollution design, and I mentioned that we want to design for a settling chamber and also on some electrostatic plates. And then we're going to move into the atmospheric or outdoor, which can also be non-point source pollution. But once it's out there in the atmosphere, how it's going to be traveling or moving around the fate and transport, which will make it more like non-point source pollution. So the distribution in the atmosphere, it's the second part. The first one is point source pollution, and the problem is about point source pollution. Alrighty. So we have this settling chamber that is going to be designed to remove 50 micrometer particle diameter, and we know the density. And we need to design a chamber that can theoretically remove 100% of that type of particles. Okay. And I also mentioned that the part A is going to be helping us to learn how to do design, and part B is going to do evaluation of an existing system. So let's see what's that about. All right. If you do, and if you have taken geology or, well, I don't know in geology, but I know that in geotechnical engineering class, you are also going to be talking about Stokes law. Just in case that you haven't, I'm going to put in here, so we're solving part A. And to solve part A, we need to use Stokes law. And Stokes law says that to calculate the vertical velocity of a particle, we need to know the gravity, the density of the particle, minus the density of the media where the particle is present. In this case, we have air. If we were in water, then this will be water. So this is density of the fluid. Okay, so just make sure that you notice that. And times the diameter of the particle to the square, and then divided by 18 times the dynamic viscosity. So all of these together can help us to do the calculation of the settling velocity of the particle. In this case, we know the diameter is 50 micrometers. We just need to give you some of the information. Based on temperature, you're going to be able to find the dynamic viscosity and the density of the air. I'm going to give you the values right now. But if you don't have them, you just need to go to a table that gives you some properties of the air as a function of temperature. So for the density of the air today, we're going to use 1.2 kilograms per cubic meter, and the viscosity is going to be 6.66 times 10 to the minus 2 kilograms meter hour. Okay, so remember these are givens. I'm giving them to you right now. On the test or the quiz, if I don't give you a table, I should be giving you these values. So you can do the calculations. This is not to memorize for. So let's check. Do we know the gravity? The value of the gravity? G.
Yes.
Yes. The density of the particle?
200 kilograms per meter cubed.
Yes, it's given. The air, I gave it to you. The diameter of the settling, the particle that is settling. If it's settling, is that what we are removing it?
50 micrometers.
Yes, we know. And then we know the viscosity, so can easily calculate yes. So gravity in metric is 9.81 meters square second times 200 kilograms per cubic meter. These design problems are very simple. It's more to understand what we have and make sure that the units are consistent. Now, diameter is going to be in meters, or particle is 50 micrometers, so it's going to be 5 times 10 to the minus 6 meters, and this is a square. All of this divided by 18 times 6.66 times 10 to the minus 2 kilograms meter hour. Okay, and then we need to do some conversion here because the meters per second square. So let's get rid of the hours and we can do the 3600 seconds. And if we do that, what is the settling velocity? The settling velocity of a particle like this usually is in meters per second or meters per hour.
Zero 0.146.
0.146 meters per second. Can someone verify the number? Okay. I don't know why it's taking so long.
I got 0.000146. So three zeros, 146.
That sounds very, very small. Are you squaring the 5 times 10 to the minus 6?
Yes, I am.
We need a third one.
Oh, wait, no, yeah, 0.000146, my bad. So there's point, and then there's 3 zeros. So it would be 1.46 times 10 to the fourth, negative fourth meters per second. My bad.
1.47 times 10 to the minus 4.
Yes.
And everybody's okay with this?
I got that as
Yes.
well. Alrighty, so let's move on. Okay. Okay, so now we have the velocity. So as you can see, the velocity is dropping down very, very slowly. It's very small number. Everybody got the same number. All right. I honestly have a different number, but we're gonna go with your calculation. We'll see what you get. Alrighty, so it says that we need to calculate the length of the chamber. So now we have the velocity. The length of the chamber is gonna be a function of this velocity. Because why? Well, let's make a drawing of this. Let's try to understand how this vent is gonna be looking like. If you remember, like vents are gonna be long tunnels inside of the buildings, and if we have particles that are going to be traveling in the air, they're going to be pushed by the airflow through the vent. Right? If there is some bigger particles that come in, they're going to be precipitating down and then are going to be coming down to the bottom. But they have to be heavier and not subject to, or not being able to be pushed by the flow. But those are going to be the type of particles that maybe we want to remove. And if we want to remove them, if we don't have a special settling chamber, then they're going to be accumulating here, reducing the cross-section area or airflow. So what do we do to be able to collect those particles? And not only that, for maintenance purposes, it's going to be hard to come and broom or clean this type of surface. So we need to have a chamber that maybe is accessible from without getting into the vent. So these chambers, they have different shapes. I'm just gonna be showing you kind of a general shape of a chamber. It's like the angle is supposed to be symmetric, but it's not symmetric. Okay. So it's going to be some sort of device that is going to be detached, and the particles, as the airflow goes to the duct, and there are particles coming in. The particle enters the chamber and is heavier and is going to be dropping down. And once it hits either the inclined plate or directly down here at the bottom, is collected. So whatever is in this pink area is going to be removed, and that will be our settling chamber. So we want to design for the length of this settling chamber. And this particle that I draw here that is blue, this one here, as it goes down, it's going to have a settling velocity. And that settling velocity, the one that we just calculated, is the one that is going to be driving the length of the chamber. The faster it falls down, the easier it's going to be to remove it. And the shorter the chamber is going to be. But if it is dropping down very slowly, then we're probably going to need a longer chamber. So that velocity is going to be dictating the length. Now I'm going to go to another page. Everybody's done with the drawing? I'm going to give you the equation to calculate the length of this particle. Okay, so we're going to need the velocity. Please give me the numbers. We're going to need the velocity, the flow, and other things. I'm going to give you the equation. So what is the equation? The equation to calculate the length is going to be equals to L equals to Q, the flow of the air, times N, but this N is, N is a efficiency or removal in percent. Okay, or as a percent. And then it's going to be divided by 100 times the settling velocity of the particle times the width of our system. And we know the width that was given on the statement. So, do we know Q? Look at the statement.
Yes, we do.
We know Q. Do we know the efficiency?
We would have to determine it. Oh wait, no, it's 100% removal.
It's
Right?
100%. Why? Why is 100%?
Because it's a theoretical perfect collection.
Because it's a theoretical perfect collection, so we're assuming that we remove everything. Perfect. We know the velocity of the particle and we know the width. So now we can calculate F. The flow rate was equals to, was it 1.5 cubic meters per second times 100% divided by 100 times the settling velocity was 1.46 times 10 to the, this is by memory. Is this correct?
It's a 1.47.
1.47. Almost. And then is times the width. What was the width in the problem? 2 meters? I think. Alrighty, if everything is correct, then give me the length. If it is a long number, don't be surprised. The velocity, the settling velocity is very, very tiny. What did you get?
5,102.
Okay, that's too much. 5,102.
Yeah.
I got 51.22.
Well, that's doable. So who's right? What's going on with the calculations today? What is it, 51 or 5,000?
It's 51.
Okay, yeah, we got some on the chat that says 51. Okay, so this 5,000 is not correct. If it is 5,000 what you're getting, and you calculate, so let's put it this way. What if we check the numbers and the number says 5,000? Will a 5,000 length inside of a building make sense?
No.
No. So what will I do? I will go back to the calculation of the settling velocity, double check that everything is correct, and everything is correct, then probably I cannot remove this particle 100% because it doesn't make sense. Does that make sense? This is a design problem. If you're sizing for an HVAC system and you know the length of your building and your building is a little home, then probably a 5,000 meters is too huge. And don't be scared when your calculations are correct. Simply you can say, well, this particle, if this particle is the concern, this settling chamber is not going to give you the removal that you want, either with increase the efficiency or with change of a completely different treatment system to ensure that it's removed 100%. Does that make sense? Thumbs up. This is a very practical exercise, and it's the one that is going to give you money when you are evaluating. All right. So we're going to go with the 51 since that everybody is in agreement.
Well, Professor,
Yes.
I actually got 5,000, so I was wondering if you can solve it out just to double check it.
Brock, I have a completely different velocity.
Or like 51,000. Like I got this first answer.
If you have what it's on the board,
51,000, 5,102.
yeah, if you have what's on the board, it should be a 51. So
Did you multiply by 100 instead of 1 because of the, efficiency?
Oh, the percent converted to decimal.
Yeah, so it's just 1%, so it'd be,
Thank you.
no problem.
Okay, so you guys have the problem solved?
I'm actually getting the 51,000 as well. So I
Are
don't.
you so for your percentage, do you multiply by 100% or do you multiply by 1? Because
By-
efficiency.
by 100, but then we divide it by 100, right?
Right. So because it's the efficiency of removal in percentage, you just want, because it's already a percent, you convert that to 1.00, right? If it was like 80% removal.
So what is the confusion here? I don't
So
understand.
instead of putting 100%, do we just put 1 then? Is it not in percentage?
It is in percentage. So let me tell you why. If we calculate efficiency, okay? If you calculate just efficiency with this, so what I'm doing is I'm going to be solving here. If we're calculating efficiency, what we are going to get as a result is 100 times the settling velocity LWQ. All right? So when you have this number on the question that I gave you, if you put 100 on the bottom, then you need to put 100 on the top.
I did that, but then I get 51,000. If I put 1 on top and put 100 on the bottom, I get 51.
Okay, so then we have issues with the velocity. Then we have issues with the velocity here. Because the velocity, I get a totally different number, a very small number, compared to the ones that you gave me. And I'm going with the numbers that you gave me, with my numbers. That's what I'm asking. All right, so if we solve L here, I think that is exactly the same. Solving L from this equation right here, L is going to be N times Q divided by 100 VSW, right? If you, here is 1, but then you need to divide by 100. Then you get the 51.
Well, if I just put 1 for the efficiency and then divide by 100, I get 51.
Okay. So let's keep it then like this, everyone. Don't erase. I'm not gonna erase. Just cross this one. Let's use this equation then.
Professor?
But if you, okay, yes?
I had a question. If it was like 90% efficiency, would we multiply by 90 or 0.9?
What do you mean?
Like right now it's theoretical, so it's 100%. But if it were say 90%, would we have the 90% up there, or would it be by 0.9?
So look at this, Brian. This number here is going to be the efficiency in percent, right?
Mm-hmm.
Efficiency in percent, you multiply times 100.
Mm-hmm.
Right? That's why in this number we have times 100, because I give you the percent efficiency.
Okay.
Does that make sense?
Yes, Professor?
Yes.
So in the first example, if efficiency is in percent, then it should be 5102. Right? Because we're leaving it at as a percent, which is 100. And I think what Anderson and everyone else that got 51 was doing was changing it from a percent to a decimal. That was the problem.
So that's what I'm going to this, Abraham. The one here that I'm putting the star.
Oh, okay.
We can use it as a fraction, right? 1, which is the mother of the question. If you want to talk about this, is where the other one originated. The percent comes from this equation. So let's preserve the velocity and the W, the Q, and solve from here, and then N is going to be 1, and then divided by the 100. And then you get 51 this way. Yes?
So we always convert the percentage to the fraction form or decimal form.
It's because when you multiply the 100%, that's when you get like 5,102 rather than 51.
Yes, no, but look, just understand this. If we just get BS times LWQ, this is going to be giving you just a fraction, right? To make it percent, we need to multiply times 100. And that will give you the efficiency, which will be in percent. Okay? So what I want you to do is work with this version of the equation. Okay? So you have 51. And so now, where is this equation coming from? From the vendor. Your a settling chamber person working on HVAC is going to be having different of them. All of them are going to be a base of the flow rate and the velocity of the particle. It has to be there. The flow and the velocity of the particle have to be incorporated. The geometry is going to be incorporated somehow too. And if you we talk about water, we call it surface overflow rate, but it's just a study of the surface of the settling of the velocity particle in a given in a tank. But in this case, we don't have a tank. In this case, we have a chamber where the particle is going to be moving in this direction. All right, and that the flow, the particle is settling down vertically. That's what I want you to keep in mind. So don't make sure that we move on in here. Use this equation. We're going to be using this. Okay? So, and if you do this, if you use this equation, if you can think about algebra when you're going to be eliminating something, if you multiply both ways, then you get rid of it and just work with this. You were asking the fraction. I think that would be an easy way to look into this equation. All right. So let's work with the 51. We'll do a 51 meters length of the chamber. I still think that it's slightly big. We're just gonna complete the problem with the 51. But this sign has this catch. This sign is a triangle. If you suspect that the steel is very lengthy, you might be looking into other particle sizes. Maybe we cannot remove 100% the 50 micrometers. Maybe we need to go and decrease the particle size, increasing the particle size or decrease the removal rate. So this will be our chamber. Our chamber will be 2 meters in width, 2 meters in height, and 51 meters in length. So we have that system, but for that system says that we also need to remove or determine the collection efficiency now of the particle that is 25 micrometers. So it's half size than the previous particle, and we need to determine the removal efficiency, the N. We're gonna use the same equation or not? Well, how are we gonna solve this problem? Well, we're gonna use the same equation, but what do we need to know to be able to use this equation here? The efficiency equation. What do you know, what you don't know?
You don't know the velocity of the wind.
Okay, so we don't know the velocity of the what?
The wind.
The velocity of the particle?
Or yeah, the particle, yes.
Okay, so we don't know the velocity of the particle, right? This is the particle velocity. Do we know the flow? It's the same dot. We know the length and we know the W. Now we know it. So if we want to determine this, oh, hold on, we need to do the velocity first. All right, we need to determine the velocity first. To determine the velocity, we are going to do the same thing. 25 micrometers, and it's gonna be equals to 9.81 meters per second square. The same density is gonna be 200 minus 1.2 kilograms cubic meter. Now the diameter is 25 times 10 to the minus 6 meters squared divided by 18 and 6.66 times 10 to the minus 2 kilograms meter hour and 1/36. Oh, this is seconds, right? 1 hour second. All right. What did you get? Oh, it's fading already. Velocity?
I got 1.25 times 10 to the negative 14. That doesn't seem
That doesn't seem correct. Okay, 25 micrometers is equals to what? Is my number correct? Is someone checking my numbers on the board?
I got 3.66 times 10 to the negative 5.
That's what I got.
Okay, are you squaring the minus 6? 25 times 10 to the minus 6 square?
Yes.
Why do I have larger velocities than you if I have exactly the same numbers? Can you check my board? Check the board. Forget about...
Wait, Professor, is it 25 times 10 to the negative 6 or 2.5?
No, it's 25. My particle is 25 micrometers. Look. 25.
Okay, then that number isn't correct then. I'll redo the calculation.
Okay, so probably we did the same thing with the previous one. That's what I was thinking, that maybe, did I put 5 times 10 to the 6 or 50 times 10 to the minus 6?
I got 3.6 to negative 3.
Okay, that sounds way better.
You put 5 on the last example.
Okay, there you go. 3.6 times 10 to... So let me put this one down. Times 10 to the minus 3 meters per second. Is this correct?
Yeah,
Yes,
that's
I
what
got
well, that's what I got.
Okay, so don't panic. This is correct no matter what. And I put 5. That's why the number was so small. So that's why we need to check my numbers, okay? I'm gonna go to the previous page to look at what I put. Yep. And noticing here, I put 55 times 10 to the minus 6, but I put the 50 here. So always check my numbers. I made a huge mistake. I'm just gonna stick in here the 0 and then give me the number. That will modify the length. I'll redo it next class. We need to start the quiz. But if you can just give me the velocity here, probably it's just gonna be slightly, how many times? 100 times?
So would it be 10 to the negative 2?
Yes. 1.47 times 10 to the minus. Is that correct? Just double check.
Yes, it is.
All right. So I'll work the length of the chamber next time. The velocities are correct now, and we discover why. Important. This is the most common mistakes in design, by the way. Anyways, let's go to get ready for the quiz. Let me stop sharing. Alrighty. You can go now to Blackboard. You remember you can use your reading notes. And what do you see? Are you looking at my Blackboard? Okay. So the quiz is gonna come soon. You don't have to submit any